students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as thermodynamics. Let's understand what is internal energy. Let's understand what is internal energy. Now, internal energy is defined as the total of all different forms of energy associated with the system. Internal energy is the total of all different forms of energy, associated with a system. Right? So all the different forms of energy that are associated with a system combined together, sum of all of them is called as internal energy. Now when we talk about internal energy, there are two types. There are two types of internal energy. One is called as kinetic or thermal energy. And the other is called as bonding or potential energy. Right? Now, so those are the two different types of internal energy. Let's try to see each one of them in detail. Let's first understand what is kinetic energy. Kinetic energy is also referred to as thermal energy. Kinetic energy is also referred to as thermal energy. Now when we talk about kinetic energy depends upon the temperature. The kinetic energy which is present in a body depends on temperature. When we talk about kinetic energy is nothing but the sum of three different types of energy. It is made up of three types of energy. It is of three types of energies. Right, first is translational energy. What is translational energy? The energy which keeps the molecules continuously in motion along a straight line is called as translational energy. So kinetic energy is because one of the energy of it is translational energy. What is translational energy? It is the energy that keeps the molecules. It is the energy that keeps the molecules continuously in a motion in a straight line. Right? That is translational energy. So kinetic energy, one of the components of kinetic energy is translational energy. The other component of kinetic energy is vibrational energy. What is vibrational energy? It is the energy associated with the vibration of atoms. Right? So the energy which is associated with the vibration of atoms in a molecule is termed as vibrational energy. It is the energy associated with vibration. It is the energy association with vibration of atoms in a molecule. Right? That is your vibrational energy. The third component of kinetic energy is rotational energy. What is rotational energy? It is the energy that is associated with the rotation of atoms in a molecule about a particular axis. The energy associated with the rotation of atoms in a molecule about a particular axis. That is called as rotational energy. So when I add all of that, what I get is called as kinetic energy. Kinetic energy is the sum total of translation energy, vibration energy and rotational energy. The next type of energy we said about internal energy was the bonding energy or potential energy. Bonding energy, also referred to as potential energy. What are the components of bonding energy or potential energy? Now, bonding energy is made up of two. It's made up of two components. It is of two types. The two components of bonding energy are intramolecular energy What is intramolecular energy? It is the energy required to break the molecule into atoms. The energy required to convert the molecule into its constituent atoms is called as intramolecular energy. It is the energy required to break the molecule into its constituent atoms. That is intramolecular energy, right? Then you have the other component of bonding energy is intermolecular energy. What is intermolecular energy? It is the energy required to separate one molecule from another in solid or liquid state. If I have two molecules bonded to each other, how much energy would be required to separate those molecules out? To remove one molecule from a crystal lattice of solid or liquid would be called as intermolecular energy. Fine? So the energy required to separate one molecule from another in solid or liquids. So the sum of intramolecular energy and intermolecular energy is called as bonding energy. Thus, total energy or total internal energy is nothing but sum of kinetic and bonding energy. Kinetic energy is translation energy plus vibration energy plus rotational energy, and bonding energy is intramolecular energy plus intermolecular energy. Fine. Next, internal energy. Is it a state function? If you remember, I had explained to you what is state function. State functions are those functions which depend only upon the initial and the final state and do not depend upon the path taken to change from the initial to the final state. So is internal energy a state function? Let us try to find this out. Now, if I plot a pressure versus volume graph. Let's consider volume on x-axis and volume on x-axis, and let's consider pressure on y-axis. Right? If I plot position A, where I have P1, V1 and EA, where EA is the internal energy, changes from A to B. The system changes from position A to position B, where you have P2, V2 and EB. Right? Internal energy B. Now it can change from position A to position B either by taking path 1. The system can change from position A to position B by taking path 1, where my change in internal energy will be nothing but EB minus EA, right? Or it can change, the system can change from position A to position B by taking path 2, in which case again my change in internal energy will be EB minus EA. That means irrespective of whatever path is chosen, my change in internal energy remains the same. That means my change in internal energy is independent of the path. That means my internal energy is independent of the path. Hence, internal energy is a state function. Right? Let's write this down. When pressure versus volume graph volume is plotted, let the system at state A, let system present in initial state A have pressure, volume, and internal energy as P1, B1 and EA, right? And when it is changed to final state B, when it is changed to final state B by path 1, its pressure, volume and internal energy be P2, V2 and EB. Right? Now, therefore I can say that the change in internal energy as the system moves from initial state A to state B, the change in internal energy is going to be nothing but EB minus EA. The change in internal energy is going to be EB minus EA. Now let us assume that the system goes from B to A. Let the system go from final state B to A. System go from final state B to initial state A by path 2. Right? I'm changing from final to initial state. Since I'm reversing the path, my change in internal energy will be negative. If I'm considering A to B as positive, that means B to A has to be negative. So negative internal energy is going to be nothing but final state now will be EA, initial state now will be EB. Right? Now, the change in internal, it has been observed that the change in internal energy in both the cases is the same. If negative change in internal energy is EA minus EB, therefore I can say that change in internal energy is negative of EA minus EB. We'll call this as E bar so that we can show you the change. So this is going to be again EB minus EA. Therefore I can say that delta E is equal to delta E bar. That means change in internal energy from path 1 is equal to change in internal energy from path 2. Therefore, I can say that internal energy is a state function. Fine, do you get this in here? Next, let's see the next thing, Hess's law. Now, Hess's law states that the total amount of heat energy absorbed or evolved in a reaction depends on the initial and final state of the system and is independent of the path followed for the change. Guys, let us try to understand this. Let's assume that a system is at state A. Okay, this is my initial state, this is my reactant, this is the initial state. Let's assume that it follows a particular path and changes to say D, which is my product, right, which is my final state. Now either a system can go directly from A to D or and have, say this is my path 1 and here the change in energy is say delta H, right. Now let's assume that instead of directly going from A to D, the system first goes from A to B, right, where the change in energy is delta H1, change in enthalpy is delta H1. Then from B it goes to C, change in energy is delta H2. Then from C it goes to D, change in energy is delta H3, right. What Hess's law says is that whether I go from A to D or I go from A to, if I directly go from A to D using path 1 or I go from A to D by using A, B, C, D, the total energy will still remain the same. That means Hess's law says that delta H will be nothing but sum of delta H1 plus delta H2 plus delta H3. That is what is Hess's law. Hess's law states that the total heat evolved or absorbed in a system depends only upon the initial and the final state and is independent of the path.
It's
right?
like internal energy.
Enthalpy.
No, I mean it's like internal energy only.
Yes.
Because even if it is independent of the path.
Yes. Even internal energy is independent and this is also independent of the state. Right? So the law states, first let's write the law down. The law states that the total amount of heat energy evolved or absorbed, the total amount of heat evolved or absorbed in a reaction depends only on the initial and final states of the system depends only upon the initial and the final states of the system and is independent of the path followed by the system and is independent of the path followed by the system. Right? That is what is Hess's law. Once you have Hess's law, let's see the experimental proof of Hess's law. That was the law. So let us consider that a substance changes from A to D by two different ways. Let us consider that a substance changes from A to D. Right? A substance changes from A to D in two different ways. First method, the direct conversion. Direct conversion from A to D. If I have direct conversion from A to D, A is getting converted into D. The change in enthalpy, let's assume, is nothing but minus Q joules. Let's assume that minus Q is the amount of heat energy that is evolved in the reaction. Right? Second method. A is converted into D in 3 stages. A is converted into D in 3 stages. Right? First, A gets converted to B. Let's assume that the change in enthalpy is minus Q1 joules. Then B gets converted into C. The change in enthalpy is minus Q2 joules. And then C gets converted into D. The change in enthalpy is minus Q3 joules. Right? Now, according to Hess's law, enthalpy change for a chemical reaction is independent of the path. According to Hess's law,